I wanted to go over a couple of problems on the second exam for you because I have a feeling that similar problems will emerge in the final exam. So let's start out by taking a look at this, I thought, pretty simple problem that had to do with calculating some OR probabilities in this case. This is essentially what the problem asked for. You had a poll asked people if college was worth a financial investment. The poll also asked the respondent's gender. This table shows a summary of the responses, and they're asking you to complete part A and part B. So part A says, if a person is chosen at random from the group, what is the probability of selecting a person who said either yes or no? So this is an OR probability problem. OR probabilities are simply figured out by adding up the two probabilities that make up the OR probability and subtracting from that sum any intersections between the two probabilities. In this case, however, there are no intersections, right? Because you are either no or yes. There's no instance here where someone is both yes and no at the same time. That doesn't even make any sense. So the OR probability is simply the probability of being a no plus the probability of being a yes. And that would be 101 divided by 1292 plus 994 divided by 1292, which equals, if I pull out my calculator, that is going to equal 1095 over 1292, which equals 84.8%. So really straightforward, very simple problem. There was another part to this problem that says, are saying yes and no complementary in this data set? Explain. So the correct answer is that no, they are not complementary because complementary probabilities have to add up to 1, and these probabilities would not add up to 1. In fact, you can see they add up to 84.8, 0.848, because it's also possible that someone is unsure, and these two cannot be complementary. Therefore, this one, 101 and 984, cannot be complementary because they don't account for all the possibilities. Here's a similar problem. In this particular case, we're asked to compute the probability of selecting someone who is female or who said no. And there's this bunch of people asked me about what this means here, and I think it just sort of complicates things. I don't know why they bothered to put that in there. The or is enough. So who is female? This group here is the group which is female, and that totals up to 723. So that's 723 divided by 1254. And now let's add in the ones who said no. That would be this group over here. They total to 91. So let's add in the 91. But you'll see here we have an intersection between no's and females. So we have to subtract that. Otherwise we count it first in females and then again in the all group, and we don't want to count it twice to get the correct answer. So we'll do 46 over 1254, and this is going to equal 768, which we will divide then by that 1254, and that's going to give us a probability of 6124, which we will then round because the exam is picky about rounding to to 0.61. It says round to 1 decimal place is needed, so 0.61 would be the correct answer for that one. Okay, that takes care of, I think, the problems that I wanted to go over from Chapter 5. Actually, there are a couple of problems I'd like to go over, a couple more problems from Chapter 5 I'd like to go over. Let's take a look at this one. This one has to do with complementary probabilities. I find that it's really helpful to write out what's actually stated in the problem, just in my own handwriting, so I get some idea of what's going on. So, fewer than 4 mistakes, probability equals 0.31. Between 4 and 10 inclusive, so that would mean 4, 5, 6, 7, 8, 9, and 10, the probability is 0.23. So the first question, what's the probability that a student makes more than 10 mistakes? All right. Well, if we know that 0 to 4 is 0.31 probability, 4 to 10 inclusive is 0.23 probability, then the total here of between 0 and 10 mistakes is going to be 0.54. And we know that the rule, the complementary probability rule, is that there can only be a total probability of 1. So we're going to take 1 minus 0.54, and that it will give us 0.46. So the remainder, that the student makes more than 10 mistakes, has got to be 0.46. Again, all the possibilities have to add up to a probability of 1. Fewer than 4 mistakes, 0.31. Between 4 and 10 inclusive, 0.23. So between 0 and 10 mistakes, probability of 0.54, and what's left over for more than 10 mistakes is 0.46. So that would be the answer there. What's the probability that a student makes 4 or more mistakes? 4 or more mistakes. Well, we know that the probability of making between 4 and 10 is 0.23. The probability of making greater than 10 mistakes is 0.46. That's annoying me. So we add those up. That's really annoying me. And the probability is 0.69. And then finally, we've already solved this problem. The probability that a student makes at most 10 mistakes, is simply the probability that he or she makes between 0 and 4 mistakes, fewer than 4 mistakes, 0.31, or between 4 and 10 mistakes, 0.23. So the probability that that student makes at most 10 mistakes is 0.54, right? It's really just a question of remembering the rule that all the probabilities in a system have to add up to 1. Which two of these three events is complementary? You have a choice of 4 or more was one answer choice. At most 10 was the other answer choice. More than 10 was the other answer choice. Again, the question was which of these probabilities is complementary. The answer can be, of course, would have to be more than just one answer. These two are complementary because these two account for all the probability in the question. So that would be another example of working with complementary probabilities. The ones I selected to go over are the ones where a whole bunch of students had difficulty. Let's do another one now. Okay, here's another problem where you don't have to do any calculating, but you just have to understand what's going on in the question here.
It says, the table below summarizes results from a survey that asked about political party affiliation and self-described political orientation. A person is selected at random from the sample summarized in the table, and we want to find the probability that a conservative person is a Republican. The probability that a conservative person is a Republican. So really, if you remember this, this notation, this little sign over here, that little solid bar, means given that. We read this as given that. So the question here, we want to find the probability that a person is that a conservative person is a Republican. So given that someone is conservative, what's the probability that he or she is a Republican? So the correct answer would be this one here. Given that they are conservative, we want to find the probability that they are a Republican. So it's as simple as that. This would be, we can find the probability that someone is a conservative and a Republican. That would be this group over here, conservative and Republican. The probability that someone is a conservative, given that they're a Republican, okay, assumes that the starting point is they're a Republican. But it says here, we know at the beginning that the person is conservative. So choice C would be the correct answer. Finally, let's take a look at this one. The table below summarizes results from a survey that asked about political party affiliation and self-described political orientation. If a person is selected at random, is the event that he or she is in this other category over here, is that independent of the event that he or she is a moderate, this category over here? Well, the way to think about this problem is to say, if I know that the person is in this other category, does that give me any insight into knowing whether or not he or she is moderate? Well, it does, actually, because I can see that it looks as if most of the people in this other category here are in fact moderate. So if I know that you are other, the best guess that I can give about whether you are liberal, moderate, or conservative, my best guess would be that you are moderate, because most people in this other category are in fact moderate. That means that other and moderate are not independent. It means that other and moderate are not independent because the probabilities are not equal of being other and independent. So the correct answer is answer D. And that's, I think, really the best way to think about problems like these. And that's really also essentially what this idea of independence and dependence is all about. If I know one thing about you, does that give me any ability to predict something else about you? And in this case, and I think in most cases actually, it does. Sometimes when you have an artificial example, throwing a dice, flipping a coin, drawing a card, the events will be independent of one another, because knowing that I just picked a queen, for example, a face card, for example, from a deck of 52 cards, if I put that card back into the deck and I'm sampling with replacement, knowing that that card was a queen doesn't help me predict what the next card is going to be if I replace that queen in there. If I don't replace the queen, then I do have some ability to predict whether or not the next card is a face card, because I have now one fewer face card. So in that instance, without replacement, the two events would not be independent. But my larger point is that when you see a table like this and it's real data, probably, you got to check, but probably the two events are going to be dependent. Only in these, or mostly I should say, in these artificial situations are they going to be independent. And in those cases, only when we're doing something, with replacement. Okay, that covers us for Chapter 5. we'll go on to chapter 6 in another video.